Hello everyone, welcome back to my YouTube channel and welcome to this very interesting section playlist on the YouTube channel related to advanced power system analysis. As you must be aware, we are talking about small signal stability, and in the previous session, I have a very good speaker, a very knowledgeable person, a guest speaker, and I have Professor Jose Luis Rueda from TU Delft. And in the previous session, he was talking about small disturbance or small signal stability for rotor angle stability. The previous class was dedicated to the basic concepts, and especially he he talked about what we know as eigenvalues analysis. Okay, this is the second part. This is the continuation from the previous lecture. And today he will keep talking about small disturbance, small signal analysis for rotor angular stability, but the focus today will be a bit different. He will be talking about small signal analysis, but using or using measurements in order to identify oscillation modes. Okay, that is what we call measurement-based methods. Thank you again, Jose Luis Rueda, my colleague and my close friend, for accepting this invitation. Okay, but before he start the presentation, I would like to do a very short presentation. Professor Jose Luis Rueda has been very prolific on academic and research output. As you can see here, there are at least 4 books. Starting from 2014, 15, sorry, with power factory application for power system analysis. Then he published advanced smart grid functionalities based on power factory, and then dynamic vulnerability analysis assessment and intelligent control for sustainable power system. And most recently, there is a book from Springer, and that is probabilistic reliability analysis of power system. This is a brand new book, 2020, that you can find at the bookstore and or on demand on Springer. Okay, a very short introduction about Professor Jose Luis Rueda. He is assistant associate professor tenure at Delft Delft University of Technology. He is associate professor of intelligent electrical power grids at the Department of Sustainable Energy at Delft, Netherlands. Also, he is the chairman of the working group on modern heuristic optimization under the IEEE PES analytic method in Power System Committee. Also, he is associate of the Swarm Evolutionary Computation Journal, Elsevier, that has an impact factor of 3.893. And since October 2017, he is a member of the Technical Committee of Power and Energy System of the International Federation of Automatic Control. Dr. Jose Luis Rueda has been very prolific. He is a young talent at Delft University of Technology. He has many publications, as you can see over here, more than 90 publications with an impact factor of 18. Also here, I have included his contact details if you want to have more interaction with Dr. Jose Luis Rueda, okay? Well, I think it's time that I give the stage to Jose Luis. And again, thank you, Jose Luis, for having this very important lecture about a small signal rotor angular stability. We have received many comments and it has been extremely positive. Well, it's the stage is all yours. Thank you, Jose Luis.
Thank you, Francisco, once again for inviting me to this series of online lectures. And today I am going to follow on the topic of small signal stability. Now, from the point of view of measurement-based methods, we have three topics. First, we will do a short introduction to wide area monitoring systems. Then we follow the basics of spectral analysis, and we finish with some basics and example with prone analysis. The ones. So, as we can visualize in this example, there are different levels of monitoring and hierarchical control actions across a power system. And this involves a number of applications in the control room. For instance, to monitor different variables that give an indication or from which knowledge can be extracted about the performance of the system, and also to perform control actions and protective measures. For the wide area monitoring system, or the basic idea is behind the use of synchronized phasors, which are given by the so-called phasor measurement units, which sample or create synchronized samples in time of different phasors across the power system. In our case, we will need to get signals for this kind of analysis for phenomena like electromechanical oscillations, which usually happen in a time frame of a few milliseconds to a few seconds, which is relatively slow compared to those two magnetic transients. It is good to have an overview of the timing of different processes involved in this, like the time for PMU measurement, fiber optic communications, the power data concentrator, and other steps. Here we can see in this example table what are the time delays involved in these processes, and in total the timing or the time delays to have a closed loop with wide area monitoring, protection, and control ranges in the order between 167 to 270 milliseconds. That is depending on each system. Of course, having a smaller time delay will be best, so we avoid adverse impact on the performance of our wide area control actions. In some recent researches, like in the Migrate H2020 project, there were some achievements in that direction. Some time delays lower than 150 milliseconds were observed. Before we go into the fundamentals of the methods, it's good to have an overview of where and how we will use them. This schematic summarizes or represents this closed loop of a wide area monitoring and control scheme. So if we go to the left, so we have representation of our system from which we have different phasor measurement units installed into it. And this is sending measurement data to through our communication infrastructure, and then we use this data for two purposes. One is to perform situational awareness, and this is the part where we will apply the example methods that we will learn today, or even other more advanced methods, to do either pre-contingency assessment. So before a disturbance occurs, we are trying to anticipate what could be the performance of the system, or post-contingency in real time. This is once a contingency occurs, we're trying to react during the occurrence of that disturbance. This situational awareness involves algorithms that should process and give indicators very quickly to have an indication of the stability performance, like for instance, what is the frequency and damping of dominant oscillations. Then, because these algorithms should perform really fast, so we don't want to have this total time delay of between 160 to 200 milliseconds to be significant increases. We need to have something that is really having a very small computational burden. Many algorithms for this are then relying on a lot of simplifications to ease the computational effort. And for this purpose, it's good to have an historical database that could help us to develop, for instance, some rules, to give some feedback, or to supervise these algorithms to perform better. Then, once we have indicators through the situational awareness stage, we go to visualization in the control room and to have some decision making by the operator. But we could also have, for some cases, automatic control actions for either corrective control or preventive control. Now let's go to the spectral analysis. As we saw in our previous lecture, we can do the analysis of the small signal stability from two perspectives. One is based on the state space model, which resorts to a linearization of the dynamic model of the system with the differential and algebraic equations, or by using a method to extract information of the parameters of the oscillations from signal records that could come from offline simulations or real measurements from the system. One of these methods is the Prony analysis, which is basically fitting a series of weighted exponential functions. How this is done? So, for the second case now, the measurement-based approach. In this example here, we visualize the fact on the top of the figure that you see now. We visualize the fact that we can have a number of measurement units that are assumed to be properly located for this kind of phenomena. So this means the measurements we're getting here always give us warranty that we could always extract information of the dominant oscillation, like the frequency and damping ratios, with high confidence. This information, these measurements, are sent through to the data concentrator, and from this we do some analysis for real-time applications, for instance. After processing this data, which could mean we could have some filtering or the trending of the data, or could be also repairing the data in case of missing some points or some samples. After doing this processing, then we can apply a so-called model extraction algorithm, like the Prony analysis. And lastly, we could cross-check these outcomes with what we have in our statistical or historical database, just to corroborate that we are not having false positives or false negatives. Once this is done, we will proceed with the visualization of confident data. Then this is the alternative. So when we don't have real measurements, so we will do it with a offline software simulation. Could also be with a real-time simulator, but the approach is essentially nearly the same. We need to have a good model of a power system that represents as close as possible our real system. That means validated models of all components. Then with this model, we'll go to a software platform in which we will select a given operating condition and an electrical disturbance. And then we will run time domain simulations. And then with these simulations, we will generate a number of signals that represent the dynamic evolution of the different variables of the system. And then from this, we will select some pieces or signal records to do the application of the model extraction algorithm. And then we will have visualization and analysis. So before going into the methods now, it's good to refresh a bit about the electromechanical oscillations. What are the typical oscillation frequencies, depending on the mode. So we have modes of relatively very low frequency that are usually inter-area oscillations in the range between 0.5 to 0.7 Hertz. Other oscillations in a range between 0.4 and around 1 Hertz are more localized within a synchronous area. And local oscillations are of higher frequency range, up to 2 Hertz, which are usually oscillations of a power plant against the rays of the system. But there could also be oscillations inside or within a power plant in the range of 1.5 to 3 hertz. What is the problem of having poorly damped oscillation? Poorly damped means the oscillations could be sustained over time or could have a growing amplitude. They can cause different adverse consequences in our system, like equipment damage, like transmission line outages, islanding, blackouts, and so on. When doing the identification of the parameters of electromechanical oscillation, it's good to be aware what type of data and which time windows we are selecting to do that. So what type of data means basically whether we have measured data when the dynamics of the systems are excited just by very small or almost not negligible increments that could be even confused with noise. This is ambient data, and this example is due to the continuous gradual variation of demand, for instance. So there's no major disturbance exciting the dynamics of the system. Even in that conditions, some oscillations could be excited. And then in that case, for ambient data, then we need a different method that with respect to the PRONI, which requires a highly excited dynamics. So this means we need a severe disturbance, like for instance a short circuit in the system. And when that happens, then the oscillatory behavior is highly excited, and we can have what is called ring down, which means oscillations of half amplitude but with decaying amplitude. There's also the ring up, could be high amplitude but growing. In those kind of signals, ring down or ring up, we can apply PRONI because the dynamics are sufficiently excited that we could do a better fitting with a simpler model, mathematical model. In the case of ambient data, we need a more sophisticated approach, which could be some autoregressive model, for instance. This is again to illustrate the ring up signal, so it's growing, the ring down is decreasing. And the idea here is to fit a model into these signals in a portion of the signal to identify the model parameters. In this example, we have the prototype signal that is using PRON analysis to identify the nominal oscillations. That means the frequency, the damping or real part, and then we have the phase shift and the amplitude of the dominant mode. In these examples here, it's good to illustrate some typical situations in which we can have what is called non-stationarities. If we go to see to the left, it seems that in the beginning the signal has a tendency to have decreasing damping, and then it seems that at least two oscillatory modes are dominant there. Whereas after 15 seconds, the oscillation starts being undamped, and then also it seems that something changed in the frequency and damping of these dominant oscillations, probably due to a change in the system, like a topological change or an adage of an important generation unit that was having an active role in the damping of this oscillation. Somewhat similar in the second case in the ring down, but this is less critical because the speed of the variations in the oscillatory modes, in the frequency especially, and the damping is decreasing. Is increasing, sorry. The oscillations are more heavily damped towards the end. Then we would like to know then how to estimate the parameters of the oscillations. First, what we could at least expect to have is to at least know what is the frequency of the dominant oscillation. And in our case, we can do that now by using spectral analysis, which has the principle or the idea of estimation of the power spectral density, which characterizes the content of the frequency content of a given signal record There are different methods to do this PSD estimate, power spectral density estimate. We have non-parametric methods like the Walsh method, parametric methods like the Ewell-Walker, and subspace methods like the eigenvector method. And some of these methods that I have just mentioned are appropriated for identification of the model parameters from ambient data. This is basically a problem of fitting a stochastic model. In the examples that we use in the lecture of today, we use the Ewell-Walker method to estimate the power spectral density from ring down and ring up transient signal records. It's important for the time being to highlight that there is a very nice report by a special task force that of the Power System Dynamics Subcommittee of the IEEE that summarizes all the findings or developments until the year 2020 at least in the area of identification of electromechanical modes. And this report covers all methods for ambient data and also for ring down and ring up. You can get more detailed descriptions there. In the case of the Ewell-Walker method, it is an autoregressive model that is used to estimate the power spectral density. And MATLAB is implemented and available if you look for the P-Euler function, which has as inputs the vector of the time series, or that means the signal record you want to analyze. And then you should define the order of the autoregressive model that is going to be fit into this piece of signal record. Also, the range of frequencies in which you want to have the power spectral density to be estimated, and then the number of samples per unit time. So in output you get the power spectral density estimate. Let's see how this works. So we have for this purposes a syntactical ring down signal in which we have one poorly damped mode. In our case, we define a threshold of 5% damping ratio as the reference to say whether it's poorly damped or not. And in our example, we build a synthetic ring down with two modes, one with 0.25 Hz and 4% damping ratio, and the other one which has somewhat higher frequency and higher damping ratio. We visualize the plot of this synthetic signal here, created in MATLAB, and also considering a sampling frequency of 20 Hz. When we apply the P-Euler function in MATLAB, we will obtain the power spectral density, and then we can plot it. It will be something like what you see in the figure to the right. So for the selected frequency range, we see that there is clearly a salient spike around 0.25 Hz, which is indeed our poorly damped mode that we created by proposing our synthetic ring down signal. You should see something like that to see dominant oscillations when using the Ewell-Walker method. To make it a bit more illustrative, in this case, we altered our synthetic ring down signal now to have two poorly damped oscillations. That could be a representative case of real systems which have more than one critical inter-area oscillation. In this case, we have two modes that are poorly damped, one of 4% damping ratio and the second one of 2%. We see that in the first figure to the left, that we see even a harmonic shape there. And to the right, we see the results of the Ewell-Walker method. And now we can see the two dominant oscillations clearly there around the frequencies that we theoretically defined when created the synthetic signal. So in this case, we can conclude that by having some signal and some signal analysis or the power spectral density calculation by the Ewell-Walker method, we could at least estimate the dominant frequencies in the system, and how this can vary in time can be also done. We will start windowing the signal records over time and then computing the power spectral density, and then we see the variation of the spectral density over time. That will be probably a three-dimensional plot. We understand a bit how dominant oscillations are varying in time, so how their frequency parameter is changing. Now let's go to the Prony analysis, which is, as we discussed before, applicable when we have a signal that is sufficiently excited. The dynamics are highly excited by a large disturbance, like a short circuit. Recalling the model that we say that is used in this case, that is a summation of weighted exponential functions, or its alternative representation in terms of exponential functions and also a trigonometric cosine function. We have to be aware of the fact that this representation, like in the equation 4 here in the slide, is a continuous equation. Whereas in our real case, we are getting discrete samples, so that means different points of time over different time instances that are arriving in our control room, or could be also a discretized signals from an offline simulation. So then we have to adjust this model to be applicable to the discrete case, like in equation 5. And then this means we have an alternative representation with this variable set. And this method, the Prony, is applicable only, as we said before, to rain up or rain down data because of the severe disturbance. And also, when checking those signals, we have to see the portions of the signals in which there is a certain resemblance with the response of a typical linear system. Also, it's important to be aware that we are going to do the Prony fitting the parameters of the oscillatory mode, like the frequency and damping ratio, should not vary within that time window, because otherwise we'll get misleading results. We have such variations. We might check if the analysis could be split into two time windows, each one having a fixed frequency and damping ratio. What is the idea of Prony analysis? So if we recall our discretized equation number 5 here, we are getting measurement samples at different time instances, which are denoted here with the character y, and then we have some numbers that are next to it within the brackets 0, 1, and so on, for different time instances. We could try to do this fitting considering all these time instances and build a so-called van der Mode problem, with the idea of trying to estimate the weights of the exponential functions of our model. By building this model, you see there is a matrix there for this variable set, from which we can have a characteristic polynomial whose roots will help us to determine the eigenvalues of the dominant oscillations, or the oscillations that are fit into this model. Then we can reassemble these equations by first considering a row vector with these coefficients of the characteristic polynomial, and then pre-multiplying with the equation that we had before with the samples of the signal. And we do that for different values of the time instances until we get the arrangement in equation 11, which is a linear prediction problem. So by using all this measured data, we try to determine the coefficients of the characteristic polynomial, which are the unknowns in our problem. So to recap, we have to target first to assemble and solve the linear prediction problem to obtain the coefficients of the characteristic polynomial. And then once we have the coefficients, we can determine the roots of the polynomials. And by doing this, by using the equation that relates this set variable with the eigenvalues and the sampling time, we can get the eigenvalues of the model that is fit into the signal record. And once we have the eigenvalues, and as we did it in the previous lecture, we can check the real and imaginary part to extract mode frequency and damping ratio. Then once we have solved then the linear prediction problem, then we can solve then the van der Mode problem to obtain the weights of the exponential functions, and from this we obtain the amplitude and the phase angle of the exponentially multiplied sinusoids that define our equation. And then we can also reconstruct the signals now that we have all the data. There are some steps to build these calculations steps in MATLAB, which are summarized here to the left. For example, a script that Francisco is going to share in GitHub probably after this lecture. And then this is code for the traditional Prony analysis as we saw in the previous slides. And this requires some input data like the sampling period and the number of sinusoidal with exponentially decaying or growing sinusoids that are going to be fit into the model. And then we get the information associated to the dominant modes that we want to get there. So we get the frequencies, damping ratio, amplitude, and phase. So we go back again to our test signal with one poorly damped oscillation, and we apply this example there. In the scripts that will be available after this lecture, there is one that builds the synthetic signal that we have here in this slide, and we used also previously, and then applies the Prony method to extract the components of the dominant oscillations in the signal. When we do that, then and also selecting a time window like the one highlighted here in this slide, which, as we say before, should resemble the response of a linear system, then we will see the results in MATLAB in the working space. So you see clearly here that in our case we asked it to have 4 modes estimated for eigenvalues in the series of the weighted exponential functions, and we saw that Prony was able to identify a complex pair of frequency around 0.25, which is the frequency of the dominant mode in our synthetic signal, and damping ratio around 4%, which also corresponds with the our synthetic signal. The amplitudes and the phase shift will probably not be identical, and this is because of the fact that we are fitting a theoretical mathematical model that differs from our actual physical system. Now, how we could relay or how we could try to test how confident these findings from our Prony analysis are with respect to, for instance, the analysis or the outcomes that we get when doing the eigenanalysis with the linearized representation of the system. It's always good to double check or cross check both results to see whether we get similar findings. You recall the previous lecture, from Power Factory, you can export the state space matrices and also other files that have the indexes of the state variables, so the order of state variables. And from this information, we can do analysis, for instance, in MATLAB. We repeat here the steps again, and we can plot again or summarize the eigenvalues for the case of the two-four machine system in MATLAB. You will remember from last lecture, we have a dominant oscillation of around 5 Hertz and 4% damping ratio, which is an inter-area oscillation that involves the machines in the 2 areas of the system. And these are eigenvalues 13 and 40 of the set of eigenvalues calculated by using the QR method. From the file, TXT file that our factory exports with the list of state variables and the order, the sequence, we can extract, as we saw just in the other lecture, the indexes of the rotor speed variables, from which we can use to extract the elements in the eigenvectors and participation factors to analyze further the oscillation. So we create a vector of these indexes to get later, as we see here in this example, for the eigenvalue number 13, that means the vector number 13, the matrix of right eigenvectors, the entries corresponding to the rotor speed deviations. This is more or less what we will get from linearized analysis. So these are complex numbers, which means we have a given magnitude and angle, and we can normalize it for the purpose of comparing later on with our outcomes from PRONIP, because we should be aware of the fact that in PRONIP we try to get also something that is comparable to this mode shape information, but will not match exactly as with the information we have here to the left. The information we have here to the left was obtained by performing eigenvalue calculations with the linearized model of the system, whereas in the case of PRONIP, we are extracting the information from a fitted series of weighted exponential functions. So it's not possible that these two match exactly. In the second case, we are getting information just from a piece of signal, whereas in the first one, we are getting information from the whole model that it has been linearized. Then, if we do the normalization from the elements that we extracted for the right eigenvector after doing eigenanalysis, we normalize with respect to the eigenvalue of the highest magnitude. So this means it's not eigenvalue, sorry, it's the element, the entry of this rotor speed component of the right eigenvector has the highest magnitude. So we will have 1 in the normalized magnitude, and the angle will be 0, and then the others are adjusted accordingly. Then from this, after the normalization, we see clearly that there is an oscillation between generators 1 and 2 and generators 3 and 4, which is what we expect from the right eigenvector, now presented in a normalized format. This is our reference for comparison later. So we're going to compare again the normalized amplitudes and phase shifts that we will take with PRONIP for the rotor angle signals. Or could also be from output power signals, and then we try to see if we have similar proportions in magnitudes and angles between the different estimated amplitudes from the different signals of the different generators. You remember from yesterday probably that this is just to refresh how we can locate information from Power Factory to locate the results and identify the dominant eigenvalues. In this case, again, we're talking about the inter-area mode, and how to get the corresponding speed entries. So we can also get these elements that we showed before in MATLAB in Power Factory. In Power Factory as well, we can run a dynamic simulation or a time domain simulation by considering an event. So we can have, for instance, a scenario of highly loading condition from export from one area to the other one, like in the chapter 12 of the book by Prabhakundar. And then we can apply a three-phase fault, for instance, in one of the ends of the timeline, and then we will see the inter-area mode oscillation excite. And we have here such example. And then we will have to perform problem analysis in some of these signals. In this case, we have the electrical power of the 4 generators. We can select the time window between 9 to 12 seconds, from which, as we saw before, one of the conditions of PRON is to have a ring down or ring up, and it should be a piece of signal in which we have resemblance with the response of a linear system. And this is the case of this time window. We can export this data to MATLAB to apply our sample script that is going to be shared later. And in Power Factory, you can just click on the plot and then select to export, and we can export it to a TXT file. Here I have shown some sample lines of code for importing this data from the TXT file exported in Power Factory, and to read the data and to assign it to a variable associated to the output power of each generator, as we see here. Due to the adaptation of the time steps when solving the differential algebra equations in the software, we have the case that the signals are not evenly sampled, which is also not okay for Prony. We should have evenly sampled signals. So to do that, then we will resample the measure or the exported signals from Power Factory. So we define a sample rate of 20 Hz, and then we calculate the time periods equivalent for the sample rate, and then we resample the signal with the spline command. And then we can also remove linear trends in the signal, and then we are ready to apply Prony. We apply the Prony model, mathematical model, to the portions of signals, in this case for generator 3, and then by doing that we get that the dominant oscillation mode is listed here, and this is the frequency and damping ratio. The frequency is very close to the one we have with linearization-based eigenanalysis. The damping ratio is relatively different because of the fitting of the Prony to this problem. Of course, the amplitude and the phase shift will not correspond to the ones that we will have for the speed entry of the right eigenvector that we determine with eigenanalysis. Then we do the same for all electrical power outputs of the generators, and we list them here, similar like we did with the right eigenvectors. Again, we normalize, and then as I say before, we compare the normalized. And here in this case, we see that there is a similar proportion in terms of the magnitude and angles of the estimated parameters for each oscillation in each generator. So this is consistent with what we saw in eigenanalysis, so we can safely say that we are getting similar findings. But again, be aware that in the case of Prony, we are just looking at one place, at one specific signal, and a specific portion of the signal to do a fitting of a mathematical model. We shouldn't expect to get all the eigenvalues of the system by just doing this approach. And the estimated amplitudes and phase shifts from Prony for the dominant oscillations will never match exactly the ones that we get from the linearization-based eigenanalysis. So be aware of that and use the two methods very carefully, eigenanalysis and Prony, and we should get similar findings. Thank you very much for your attention, and I wish you and Francisco a lot of success in the subsequent lectures.
Well, thank you, Jose Luis. It has been extremely good lecture. I think it's one of the best regarding small signal analysis, especially using measurement-based methods. I agree with several of the comments that we receive. You are presenting practical aspect using the excellent Power Factory and MATLAB and making things extremely easy. Thank you very much for your time and for being a guest in this session. And I hope that we can have more sessions coming from you in the near future. I would like to say thank you very much for your strong support, and of course you are welcome to come back to the YouTube channel and present more aspects. And to the people that is watching the video here in YouTube, I would like to say that very soon we will have more guests, and also we will keep going with the advanced power system analysis. Um, Again, thank you, Jose Luis, and thank you all of you for watching the video. Please feel free to subscribe and feel free to also to send comments or questions. We will be very happy to help you. Thank you very much. Bye now.